Hello everyone. So in this lecture, we are going to talk about measures of dispersion. Very often you will see data sets which may have same measures of center. Like for example, if I take 1, 2, 3 and 2, 2, 2, the both are going to have same mean. Um, the expected value mean is going to be um, 2, or average is going to be 2. And then here mean also 2. And then if you take the median, another central measure, it's going to be same. So, but of course, you can see that two data sets are different. On the one, uh, this data set is, you can see identical data points. And here you have some variation. So even if you graph it in a number line, you can see this one is 1, 2, and 3, and the other one is just you have uh, three three identical data points. So we want to measure how much data deviate, how much data disperse. So there are different measures. I can say the popular one is variance. In a way, that's measure how much data deviate from a mean squared. We are going to talk about the deviance, and then we square it and we take the average square deviation from mean. That will give you the standard deviation. So the notation wise, we will have something called sigma square here, and then this one is just sigma. So you have actually two types. You have population, and then you have sample. Okay. So let's go to the lecture and see what's in there. Some other measurements you can use range, which is max minus min. So this one, it's very simple way to measure the spread. For example, the one we had 2, 2, 2, then the range would be 0. And then the 1, 2, 3, range would be just 2. One of drawback of this one, you really ignore about all the middle values. You just go to the two extreme values, minimum and maximum, and then from there you take the range. Another one is taking the quartiles, like this is the 57th percentile, and this is the 25th percentile. So you take the difference. That's called the interquartile range. If you're going to create a box plot, this is very useful quantity to know. But in this class, you can just calculate these two and get their value. Okay, so what we really want to learn and what we're going to use when we go to the probability distributions are variance. That would be our discussion next slide. So variance is defined as the average square deviation from the mean. Now, deviation from the mean, that would be x minus mu. Okay. X is the random variable. So you have x minus mu. Remember how you get the mu? Mu is basically expected value of random variable x, long run average. So then you square it. So you have squared deviation from mean. Then you take the average. In probability sense, taking average means you are taking the expected value. So you take the expected value of that. Okay. There's another name for this one. If you remember from previous lecture, this is second central moment. Okay. Which you call as variance. You can expand this. So if you expand it, it's going to be what? If you expand this, it's going to be x square minus 2x mu plus mu square. You know that expected value is linear for these operators, so you can just write like this. Mu is constant, which you know, so you can take it out. And then from here, you can see that this is going to be mu. So you have 2 mu square plus mu square, which end up as this. So you can use one of these formulas. Okay, this is something you would see very often. Usually you would see this in a different way. This one is same, but the mu people write, the textbook write like this. Instead of mu, they would write x by value of x. One of very simple relationship, variance of ax plus b is a square plus variance of x. Now, of course, remember that variance of constant is 0, because if you take a mean of average of constant, it's going to be itself. So, so there's no deviation from mean. So the basically variance should be 0. This is different from x by value of constant. X by value of constant is constant itself, but variance of constant is 0. Okay. I just want you to see the difference between taking x by value of this one. That's going to be a time x by value of x plus b. But if you take the variance of x plus b, that's going to end up as a square time variance of x. Just see how the constant is being squared and then the b is not there. Okay. One problem taking variance is the units of variance is going to be squared. Okay. So let's say you measure x, observation of x measured using meter, then the variance of x, the measurement unit is going to be meter square, which is sometimes hard to, I mean, in this way you can say area, but sometimes, like, let's say kilogram square. Okay. Then it doesn't make any sense. So because of that, in order to understand really what that means, you would like to take the standard deviation. So if you take the standard deviation of this quantity, okay, so when you take this variance, you take the standard deviation. So basically, standard deviation is the square root of variance of x. This one has the same unit as the observations of that unknown variable x. So here you can see the example, and I'm going to do the variance, you can do the rest. So how do you find the variance? First, you have to get the mean. How do you get the mean? Since these are individual data points, we can think probability as how many data? 1, 2, 3, 4, 5, 6. So each one, the probability of occurring each one is 1 over 5. Oh, no, actually 6. So let me write 6. There are 6 data points. That's the probability. Okay, this is random variable x, taking each value. So you can calculate the probability based on x time probability xi. Okay, so in that mean basically 50 times 1 over 6 plus all the way up to 90 times 1 over 6. So it's similar to taking average, because we took probability as 1 over 6, otherwise it may different. So basically you are adding all these numbers. For this particular example, you divide by 6. Okay. Then you can find the second moment. Okay, I'm going to use the second part of this formula. I'm going to use this one. So how do you get the second moment? So you have to take x square. So this is x. X square is going to be what? 50 square, 55 square, 59 square, 64 square, 88 square, 90 square. So x square value of x square is going to be 50 square times 1 over 6, all the way up to 90 square times 1 over 6. Basically, 50 square all the way up to 90 square over 6. So now you can take the variance of x using this nice formula. So here there are some questions. You can see whether you can create these kind of examples. Is it possible to have two data sets with same mean but different variances? Think about it. Is it possible or no? Just think about this example. Okay, so 1, 1, 1, 2, 3, and 2, 2, 2. What do you think? Okay. Is it possible to have two data sets with different mean but same variance? Can you create a one? That would be a fun challenge. For given two data sets, if mean and variance are same, can we say two data sets are identical? Can you have two data sets with mean and variance? They are same, but are they going to be identical? The answer would be no. Okay, but see whether you can create one. If variance is zero, can we say data identical? Yes. And then if all data identical, variance is zero. If variance is zero, data identical. I mean, you can go to the formula. You can see our formula is this. Okay, that's the variance of x. So if this one is zero, the only way you can get that is x minus mu square equals zero. Okay, so basically we are saying x equal. Yeah. Okay, can variance be negative? No. The way we define it, because we squared it, so you have positive value and you're taking square root of positive value, so it's going to be positive. Okay, so this is, it can be zero, but it cannot be negative. So here you can you see another example, random variable x taking 1, 2, 3 up to 5, and the probability of taking those values and calculate the mean and variance. So use the formula. This is sigma x time probability, I mean, xi time x equal xi. Then then you take the second moment. So basically you need to have another column here, another row x square. Probability going to be same. Okay, so 1, 4, 9, 16, 25. So you multiply these two in here. Okay, 16 times 0.25, 9 times 0.17, and you add up. Then you use the formula of variance to get the variance. Do the problem and then post in discussion board so we can discuss your solution. So here you can see an example from SOA question. A probability distribution of the claim size for an auto insurance policy is given in table below. What percentage of claim is within one standard deviation from the mean claim size? So you can first find the EX and then the standard deviation, which is from EX square, and then from variance. Then from there you can get the standard deviation, which is square root of variance, and then C, which is mu, one standard deviation. Okay, so add mu plus sigma, mu minus sigma, and see how much data you can capture. Again, come back to the discussion board to discuss about the solution for this question. I gave you initial setup, but you need to do it and discuss in discussion board. So here you can see that we try to standardize random variables. Okay. Once you standardize, there are no unit, because you can see x has some unit, mu got unit, the sigma got unit, so unit you cancel out. This one is without units. So this is by once you standardize, you can kind of like compare two different populations. One of good example I use, let's say you want to compare running time in Olympic, let's say 100 meters for men versus women. Okay. One of best way you can do that, rather than thinking about gender, convert everybody's running time to standardized score. Okay. And then here you have, let's say it's y, but still same c. Okay, mu. So this is the average for women, that some group running time, runtime, and then this is standard deviation. This is for men, this is for their standard deviation. So once you have these two scores, you can compare for any person. Let's say this is for Usain Bolt, and this is for, let's say, Anne Shelley, for another top runner in women group. You can compare who's really good, because just comparing running time to one group another is not fair. You have to compare to their respective group. So now once you standardize, you can do that. So we call this as Z-score. This is very useful when you go to the normal distribution, because then all you need to know about the standard normal curve. We will discuss this later. But right now, how to standardize a random variable. Regardless what standard line distribution, you can always use this approach. So here you can see some probability bounds. Of course, at very beginning, we learned that probability for any event in which should be between 0 and 1. Okay, that's one of like a large bound. But then we can make it more precise, more accurate. So here one of that approach. So let's say you have a non-negative random variable which take non-negative values. So the image of random variable. Okay, so basically what this means. Remember what is random variable? It's sample space to real numbers. Now this one says this image of y should be non-negative. Okay, so basically subset of non-negative values. It can be real, but it need to be non-negative. This is the negative real numbers. Okay, so with finite mean. Okay, so remember that, I mean, we didn't do that kind of examples, but expected value, there are no rules saying that expected value should exist. Expected value can be infinite. Okay. So because of that, we don't know whether for given random variable, without knowing its probability distribution, it's going to be finite or not. So in under Markov inequality, we need finite mean for the random variable. So this one should be finite. Then for any given positive value, we have this bound. So probability, random variable taking value above A. Remember, random variable taking only non-negative value. So A is positive. Okay. So this probability is going to be less than or equal the expected value of y divided by A. Okay, so that's the Markov inequality. By the way, like if you create a random variable, let's say y equal 1, 2, 3, so forth. Then the probability, let's start with 2, 3. Then the probability of y equal y is going to be, no, that's not a good example. Just forget about that. Anyway, so you can use this Markov inequality to bound the probability. The other one is Chebyshev theorem. So in this one, it's again a bound. It's try to bound the probability, but this time it's used two values, the mean and standard deviation both. In previous one, we had only mean, finite mean. Now, if we know both finite mean and finite standard deviation, then we can create more better bound. So this one is saying that the probability that x is more than k standard deviation away from mean is going to be less than or equal 1 over k square. This is without knowing x distribution. Okay, remember that. So without knowing distribution of x, okay. If you know distribution of x, then you can really create a better bounds. But this is in general, you have this bound. Okay. So here k is more than 1. Um, so um, so this one is very useful. But if you take the complement of that, you would get the another bound, which is in here. Okay. It's same. Okay, you can see that if you add this one and that one, you get the probability of 1. So these are complement of each other. So what is this? This one is saying for any population or sample, at least 1 minus 1 over k square of observation in the data set fall within case standard deviation from mean. Okay. I mean, you can expand this absolute value. So let's say I expand this one. So what's it look like? It's going to be look like x going to be less than or equal to mu plus k sigma, and then here you have mu minus k sigma, and then the probability of that is more than 1 over k square. Okay. 1 minus 1 over k square. So you can do the same with this one too. So here you can see that the random variable taking value k standard deviation away from mean is going to be at least the probability of that is going to be 1 minus 1 over k square. So here you will see an example of Chebyshev theorem. So this one gives the mu 30. Sigma square is 64, so that means sigma is 8. And use Chebyshev theorem to calculate the smallest symmetric interval that contains 8% of data. So I want to calculate probability mu minus. So what is mu? Mu is 30. Let's write that in. 30 minus k times 8. The symmetric interval. That means basically same standard deviation away from mean. And then this need to be 80%. Okay, that's what we are saying. Okay. That contain at least 80% of data. So if I use this, I can see 0.2 equal 1 over k square. So k square is what? 5. K is square root of 5. So so then you can create the interval. It's going to be 30 minus the square root of 5 times 8. 30 plus square root of 5 times 8. The probability data in between that at least 80%. There's another one, coefficient of variation. It measures how standard deviation change respect to the mean. So when you analyze data, this is something very useful. You can do the problem. If not, please type the problem in discussion board. We can discuss. Okay, so that's all for this discussion.